Let us start chapter 6 module 3. In this module we shall discuss orbit spaces. So what is called orbit spaces? Let us start with an example which we have already done. We have already seen that S1 is the quotient space of closed interval 0 1, where the quotient mapping is Px is equal to e to the power 2 pi ix. There is an alternative form of S1. If we think S1 as a group under the complex multiplication, then this is isomorphic with the group R by Z, where the group operation is addition. Now let us consider the group R by Z. Observe that the group R by Z considered as the orbit space of the action of the group Z on R. How the group Z acts on the space R. Let us take an element n from Z. Then we define a mapping from R to R as follows: n of R is equal to n plus R. Then clearly this mapping is a homeomorphism. So every element of Z acts on R as a homeomorphism. Now for each R belongs to capital R, we have that n plus R such that n belongs to Z. This set is an orbit of R determined by the group Z. Now one can observe that each orbit under the action of the group Z either identical or disjoint. So these orbits gives a partition on R. Since this give a partition on R, we can get a quotient mapping and a quotient space on the set of orbits. This space can be called orbit space. Keeping this in mind, we shall define action of a topological group on topological space, and then we shall define what is called orbit space. Let us go to slide presentation. So let us start with the formal definition of action of a topological group on a topological space X. A topological group G is said to act as a group of homeomorphisms on a space X if each group element induces a homeomorphisms of the space X in such a way that G1 G2 of X is equal to G1 of G2 of X for all G1 G2 in capital G and X belongs to capital X. 1 X is equal to X for all X belongs to X, where 1 is the identity element of G. The mapping Gx goes to G of X from G Cartesian product X to X is continuous. Observe that as G is a topological group, so the third condition is meaningful. In fact, action of a group can be defined in any mathematical object. For a normal set where there is no mathematical structure except the cardinality, there the group action is determined by permutations. If we take the mathematical structure as a group, then the group actions is determined by the automorphisms. In case of matrices, the group actions are isometries, and in case of topological spaces, the group actions are determined by homeomorphisms. In fact, if we take any mathematical structure and take all possible structure preserving mappings from that mathematical structure to that mathematical structure, that becomes a group, and any of its subgroup acts on that mathematical structure. Now, let G be a group which act on a topological space X. Then the set Gx such that G belongs to capital G is called orbit of X and generally denoted by OX. One can easily observe that any two orbit either identical or disjoint. That means orbits gives a partition of the topological space X. So, we get a natural projection mapping P from capital X to the set of all orbits. The mapping defined by P of X is equal to OX. Then this projection map gives a topology on the set of orbits. With this topology, the set of orbits is called the orbit space. So, this is our example which I have already told. Let us consider the group Z and its action on the topological space R by translation. That is, the action is defined as for each n belongs to Z, n x is equal to n plus x. So, the orbit of x of this action is x plus n such that n belongs to Z. The corresponding identification space is denoted by R by Z. Now, if we set a mapping R plus Z to e to the power 2 pi I r from R by Z to S1, then it becomes a continuous bijection which is also closed. Therefore, R by Z is homeomorphic to S1. Now, we consider the action of the group Z cross Z on the topological space R cross R. What this gives? In fact, this gives our known torus. Here, the group action is defined in the way that for any m n belongs to Z cross Z and x y belongs to R cross R, the action is defined as mn of xy is equal to m plus x comma n plus y. So, under this, the orbit space becomes R2 by Z cross Z, which is homeomorphic with S1 cross S1, which is our defined way of torus. Let us recall the notion of projective plane we have previously defined. We have defined that projective plane is in fact obtained by identifying antipodal points of S2. Now, we can consider projective plane also as the space also as the orbit space obtained from the action of the topological group Z2 on sphere. Next, we consider another important topological space which is called length space. Let P and Q be relatively prime integers, not necessarily primes. Now let us consider three sphere S3 in the complex space of dimension 2, that is S3 is equal to all Z0, Z1 belongs to C Cartesian product C such that Z0 into Z0 conjugate plus Z1 into Z1 conjugate is equal to 1. Now let A be the generator of the cyclic group Zp, and let us define an action of Zp on S3 by the following rule: A of Z0, Z1 is equal to e to the power 2 pi I p Z0, e to the power 2 pi q I by p Z1. If we repeat a total of p times, we arrived at identity homeomorphism. The orbit space S3 by Zp is called a length space, which we shall write by LPQ. We shall see later that LPQ is locally Euclidean of dimension 3. The following example shows that in fact L21 is homeomorphic with the real projective plane of dimension 3. We know that Rp3 is in fact the action of Z2 on the 3 sphere S3. Also we know that L21 is an identification space of S3, the orbit space under the action of Z2. The action of the generator of Z2 is the homeomorphism defined by Z0, Z1 goes to e to the power 2 pi I Z0, e to the power pi I Z1 is equal to minus Z0, minus Z1, and we know that minus Z0, minus Z1 is the antipodal point to the point Z0, Z1. Thus, the identification space is exactly Rp3. So far in this module, we have defined action of topological group on topological spaces, and we have discussed some examples of orbit spaces. Some important examples are R by Z, which is homeomorphic with S1, projective plane, which can be obtained by the action of Z2 on S2 or S3, and length spaces. We shall also describe some other action of groups on topological spaces and some other orbit spaces. Let us go to slide presentation. Next, I shall prove one theorem regarding connectedness of a space depending on the connectedness of the topological group and the connectedness of the orbit space. This theorem will be required for our future purpose. Let G be a topological group which acts on X, and suppose that both G and the orbit space x by G are connected, then X is connected. To prove this, if possible, capital X is disconnected, then there exist disjoint open sets U and V such that X is equal to U union V. Now, since the identification map is open and since X by G is connected, we have that both PU and PV cannot be disjoint, because in that case PU union PV will be equal to X by G, and both PU and PV being non-empty open set, X by G will be disconnected. Now let us choose a point from PU intersection PV, let it be Px. Then both PU intersection orbit of X and PV intersection orbit of X are non-empty. These two sets decompose the orbit of X as disjoint union of two non-empty open sets, but the orbit of X being continuous image of X and hence connected, which is a contradiction. Therefore, X must be connected. Next, we shall prove the connectedness of the matrix Lie group SON. Consider the group ON and consider its action on the n sphere Sn. Note that if A belongs to ON and if A of E1 is equal to E1, then A has the form 0, 1, 1B, where B is an orthogonal matrix. Conversely, any matrix of this form fix E1. Therefore, the subgroup of ON consisting of those elements which leave E1 fixed is isomorphic to ON minus 1. The action of the group ON on Sn minus 1 defined by A E1 goes to A of E1 is continuous. Then the function f from On to Sn minus 1 defined by the chain A goes to A E1 goes to A of E1 is surjective. Now ON is compact and Sn minus 1 is Hausdorff, which makes F an identification map, because in that case F becomes a closed continuous surjective map. Now if X belongs to Sn minus 1, it can be easily checked that F inverse X is precisely the left coset A O1 minus 1, where A belongs to ON, satisfies that A E1 is equal to X. Therefore, the partition of ON induced by F coincides with the left coset decomposition of ON corresponding to the subgroup ON minus 1. This shows that ON by ON minus 1 is homeomorphic to Sn minus 1. By similar argument, we can prove that Son by Son minus 1 is homeomorphic to Sn minus 1. Now, So1 is a single point, and using mathematical induction we can show that each group Son is connected. So, this proves that special orthogonal matrix is connected. Let us consider an example where the group Z act on the space R cross unit interval. Let n belongs to Z. Let us define the action n of x y is equal to x plus n comma y if n is even, and n of xy is equal to x plus n comma 1 minus y where n is odd. Equivalently, we can say that n of xy is equal to x plus n comma half of minus 1 whole to the power n comma 2y minus 1 plus 1. Then the set I cross I has representatives from every orbit, and 0y is identified with 1 comma 1 minus y. The resulting orbit space is therefore Mobius strip. Finally, we give an example which shows that Z2 has an action on the torus with the orbit space as cylinder. Let us represent torus in R3. Then we define a mapping as follows: G of xyz is equal to x minus yz. In fact, this mapping gives a reflection through the xz plane. Now consider the set A is equal to all x, y, z belongs to the torus T such that y is positive. Then A is in 1-1 correspondence with the orbits. No point on the boundary of A is identified with any other point of the boundary of A or any other point in A for that matter. Thus, A is homeomorphic to the orbit space and it is obviously homeomorphic to the cylinder. Thus, we have that cylinder can be obtained as an orbit space of the action of the group Z2 on torus. So, in this chapter we have discussed about orbit spaces. We have seen that many of our quotient space can be obtained as orbit spaces, where most of the cases the group Z or the group Z2 acts on a topological space. With this we end this module, and as well as this ends our course.